Thank you very much. Thank you for the invitation. So yes, at VPI Photonics, where I will present this work. For those who don't know, it is a professional simulation software where we cover we have solutions from the higher layer to the physical layer down to the device level. So in this presentation, I'm going to show you different machine learning algorithms in this next generation coherent QAM hybrid optical wireless transmission systems and how we can improve performance by mitigating nonlinear distortions. So first, I'm going to show some trends in this field for terahertz frequencies. And then I'm going to showcase to you the VPI machine learning framework toolkit, relatively new toolkit, where we will harness machine learning for the equalization task. And finally, I will showcase this application of equalization and how we can improve terahertz optical wireless systems carrying QAM modulation format. So yes, so far we have seen substantial increasing in data rates and with 5G, but however we have been limited to a portion of the electromagnetic spectrum. So there is a need for new technologies in order to improve 5G capabilities, and one of them is the hybrid terahertz wireless communications. So this will operate in a spectral region between 0.1 to 1 terahertz, as we can see here in the figure, and it can offer wide and contiguous bandwidth. It is possible to increase the data rate from 100 gigabits per second and above for a single wireless link. And it also provides the opportunity to have coexistence with current fiber optical networks, and that's why they have been very attractive. In addition, we can add that it can also enhance network flexibility and capabilities. And terahertz wireless fiber extenders can also connect areas that lack network infrastructure due to budget, for example, or geographical challenges. So yes, the terahertz wireless link will be essentially an extension of the existing fiber infrastructure, and we can provide even terabit per second data rates, and we can also have rate convergence between in the optical and wireless domain. So this is one common approach here, taken from the German-funded project AINet Protect. So there are different applications for terahertz optical wireless communications, for example, from roof to roof of buildings. But in this one, you can imagine it can be far away from an island, or we have it between a river or a lake. So from the transmitter side, from the building, we can modulate the signal in two polarizations. So we can have dual polarization IQ modulation for QAM, and using external modulation, namely the Mach-Zehnder modulation. We can also further improve with pre-distortion transmitter digital signal processing, and then we transmit over the fiber, and this is essentially the fiber optical modem. After fiber transmission, we have an optical to RF interface, and so the signal is passing through the antenna array and then through the channel where here we take the weather conditions at a distance d. Then we have the antenna receiver, the RF optical interface, and then back to the fiber link, and then demodulation to the other building. However, one of the main problems we have seen is that the wireless terahertz channel is highly affected by channel dynamics. So essentially, this is due to the weather conditions, and this results to variable attenuation. So unlike fiber optical transmission, wireless communication above 100 gigahertz faces significant attenuation from atmospheric water vapor. Also, rain and fog will cause water droplets to absorb and essentially scatter terahertz wave, and that will result in increased signal loss. And atmospheric losses contribute to the so-called free space path loss between antennas, and this will lead to weather-dependent variation in channel SNR. So this is an example for Germany were taken from the Central European Refined Analysis version 1 for 10 kilometers raster for the year 2018. And we can see in this contour plot the more dark blue color contributes to more attenuation. So we can see initially with just rain, then with fog and cloud, we have more attenuation. And then with gas-specific attenuation, oxygen and water vapor, even more. And yes, this is a good case from experimental data taken under the framework of the AINet Protect. And this is the equivalent transmission link diagram and the simulation model we're going to implement at VPI Photonics software. So this is the virtual link architecture where it combines optical, terahertz link, and then again an optical link. So we start with a digital baseband signal. There we modulate the signal, and then through digital to analog conversion, we modulate the two polarizations with dual polarization, separate for the I and Q, and then we combine them through a standard single mode fiber. Then again, we split them to have the two coherent receivers. We include also transimpedance amplification, and then we have the terahertz analog front end implementation, where we will use a carrier frequency at 270 gigahertz. This usually comes together with some electrical amplification, and then we mix the signal for the horizontal and vertical for X and Y polarization, essentially through a circular waveguide, and then transmit through the antenna where we have the wireless channel. At the receiver side, we have some low-pass filtering, and then we will use these LNAs, which are electrical low-noise amplifier, because we need more gain due to the wireless channel loss. And then again, we have another similar optical transceiver, and the DSP is placed over here just at the receiver end, and then we are able to demodulate the QAM signal and get the bit error rate and other metrics. However, we will conduct simulations that fixed fiber loss and wireless loss, but in the wireless channel, essentially, we have a different probability of occurrence that changes over time. So this is an example from real data where we can see at about 18 dB of SNR, we have more of the accumulated of the data. And here we see the implementation over different modulation formats at 1 kilometer and what is the resulting bit error rate. So we see for QPSK, we can have lower than 10 to minus 3, which is a typical FEC threshold, but for 16 QAM, we will need a super FEC less than 10 to minus 2. And for 64 QAM, actually, we have quite very distorted signal at around 10 to minus 1. So let's check now, step by step, how we have implemented this system and how we simulate it. So first, regarding the optical front end transmitter and receiver, we use, towards this configuration, we use no pre-distortion. And we implemented for the linear RF driver 15 dB of gain, and we simulated with Gaussian distribution the noise current density. We had an insertion loss of 9 dB for the IQ Mach-Zehnder modulator and an extension ratio of 25 dB. While for the CW and local oscillator lasers, we used the fixed line width at 500 kilohertz and output power of 3 dBm. We also consider pulse shaping and all the effects in photodiode and transimpedance amplification. And to make it more realistic, we took some real data from real devices. So this one is from analog coherent optics transmitter linear driver, the frequency response. and also the frequency response. This is the S21. Also the frequency response related to the electrical optical response here of the Mach-Zehnder modulator, and also for the transimpedance amplification. So at 3 dB bandwidth, we see around 32, 35, and 38 dB, 38 gigahertz bandwidth respectively. And the same parameters were chosen at the optical front end at the receiver side, which includes here, as we can see, the receiver DSP. Now, regarding the terahertz front end, the mixer can support actually terahertz signals ranging from 220 gigahertz to 330 gigahertz, but we selected 270 here. After direct IQ modulation into the terahertz carrier, both polarization branches are multiplexed to one common circular waveguide here that can support the two orthogonal modes. So this is the vertical and horizontal for the X and Y polarization, and they're all merged into the antenna feed horn. Then this has an advantage that there is no need for a frequency duplexer, and the polarization multiplexer requirements are less stringent due to the polarization MIMO compensation we can use at the receiver and at the DSP. So the most important issue with such terahertz systems is actually at the receiver side here, regarding the linearity of the receivers. So essentially, very low receiver noise figures better than 9 dB can be realized at 300 gigahertz only if we use these LNAs, these high gain, low noise amplifiers. However, since the maximum possible LNA gain is limited by the compression of the mixer, these noise figures have to be traded off with linearity in order to maximize the dynamic range of the receivers. So actually, in this figure, showcasing the output power versus the input power characteristics for the RX mixer and LNA combined, we see actually that here it becomes nonlinear when we are driven close to the saturation point here. So when operating an electronic LNA very close to this point, which is typically near the 1 dB compression point, then the power amplifier's transfer function starts to become nonlinear. And so if we do a basic simulation here at 32 gigabits per second for different modulation formats at 1 kilometer wireless distance, we can see that the SNR required for a fixed bit error rate becomes very, very high when we increase the modulation format. Regarding the SNR calculation, we use this analytical expression first in terms of the received power. And yeah, so in this case, the transmitted power PTX will be equal to 0 dBm, for instance, and where LA is the resulting loss from atmospheric effects and the free space path loss, and is given by this equation, and where R is the propagation distance. And so this can be given to the distance here, for example, it can be 1 kilometer. So then the SNR in dB will be subtracting the received power and with the received noise, which is given by the thermal noise power plus the noise figure, which is 10 dB in this case. So, okay, so now combine all the transmitter receiver and the terahertz wireless part. So this is the combined schematic once again. So let's see now the resulting constellation diagram, how it looks like. So suppose we modulate with a 32 QAM system. So turning on all of the linear and nonlinear effects. So first, at the coherent receiver output, we will have a very noisy signal like this one. Then we recover for the polarization effects, but it's still very noisy. So then we apply a 4x2 TDE equalizer to equalize the signal and further remove other noise effects. So then the remaining is regarding transceiver noises, which is for the frequency offset, compensation, and carrier phase recovery, which we use the blind phase search algorithm. And if someone wants to make more complicated the DSP, he can even add a post equalizer of 4x4 based on the least mean square algorithm. So note that these results are for fixed attenuation related to a targeted SNR. So then, as we mentioned, we use the local oscillator at the 270 gigahertz, the carrier frequency, and then at the receiver side, due to this low in noise amplification, we have the electric amplifiers actually become nonlinear, as we can see here, when driven close to the saturation point, which is about 1 dB. And yes, so then actually the result is that if we have higher wireless link distance, we operate at the linear regime. While at a lower distance, because of this effect, we can be in the nonlinear regime. So let's see now the equivalent received constellation diagrams at the different points of the link. So first, after transmitting only a 10 kilometers fiber, we use the related receiver DSP here, and we see a quite clear constellation point only affected by the fiber effects, such as chromatic dispersion and fiber nonlinearity. Well, consider chromatic dispersion compensated all of it, so the remaining one will be nonlinearity. Then we transmit through 1 kilometer wireless channel, and you can see we have much more distortions, and they start to become more nonlinear. Then after another 10 kilometers of fiber, we see a little bit more distortion, and essentially the symbol error rate from 4e-7 goes down to 1e-2. So what is interesting now due to this plot here for the LNA is that if we use less wireless transmission channel of half kilometer, then we will see much higher nonlinear distortions, and not only that, they're no longer of Gaussian shape. They have this bin shape that affect the system, and so this is the main challenge, having this type of bin shape constellations. How we can make the DSP work effectively, because if you check on the symbol error rate, now it becomes even more distorted, reaching at 7e-2. So DSP eventually is no longer optimal, and so that's why we need to think of something to improve this effect and tackle this kind of nonlinear, non-Gaussian shapes in constellation diagrams. So for that reason, we want to harness machine learning, and we can do that through our VPI Photonics Machine Learning Framework Toolkit. So a quick review about that. So you can see here all the solutions we provide VPI Photonics. We cover from the higher layer to the physical down to the device level. And the VPItoolkit ML framework is a complementary tool that enhances our library. So at this stage, it can be implemented for the transmission and component design. So the question is, what exactly is machine learning? Well, in machine learning, we automate statistical models using some algorithms to make some predictions. But these predictions initially, they're not very good. So we adjust some of their hyperparameters, and then we make better and better predictions. And that is the whole concept of machine learning. In MLF framework, you can have flexible operation at both digital and field level. And for the complex data, we use the sliding window time domain approach, where you also have Python-based neural network interfacing. So this is the key modules here used for data extractors for the training data for the supervised algorithms. And this is the model loaders for neural network. This is an example of a deep neural network. We also provide support with for custom ML algorithms, open source, also with recurrent neural networks. And we provide also algorithms that are unsupervised, and they're used for pattern recognitions, for instance. And we have also user-friendly interface with the TensorBoard for proper visualization of the neural network parameters. And finally, seamless integration with JupyterLab for prototyping. So the first algorithm we're going to implement is the well-known deep neural network. So yes, in this one, we have multiple layers interconnected to each other, and we try to make some complex relationships between input and output. And it has been shown actually that work very well in noisy or incomplete data, and they have been implemented in many real-world applications. So these are the three input layers, one output here, and you can have the corresponding hidden layers. And this one represents a node, which is a neuron. So DNN uses this hidden layer as a place to store and evaluate how significant one of the inputs is to the output. We cover here now a regression type of deep neural network, and then through the backpropagation algorithm that use a gradient descent, like a stochastic gradient descent, then the weights are updated based on the loss calculated from the prediction of the DNN and the actual target values. So this is typically what you're going to see after the DNN is learning. And this is in terms of loss and number of epochs. Number of epochs is the number of iteration of the algorithm, and loss is a metric such as the mean square error. So essentially what we do is the inputs are multiplied with the weights after having changing the weights, and then we sum them, and we add also a bias which allow us to learn a non-zero output value even when all the input values are zero. And then finally they're passed through an activation function. This is a simple step function, but in most cases we'll use a nonlinear activation function like this one, which is a sigmoid function, and this will actually define if the weight is fired, which is essentially the neuron, is fired or not. And it also, in such nonlinear functions, will define the steepness of the function, of the sigmoid function here. And essentially, we squash the numbers to create a probability between +1, -1, or 0 and 1, and then you get your output. We have some other type of machine learning algorithms, and these ones are the machine learning unsupervised algorithms. So these clustering algorithms help us identify and group data. So essentially, this is for pattern recognition, and it has much lower complexity because no training data actually are used. So here we see some algorithms in terms of complexity. We can see usually the supervised algorithms are of the highest complexity. And regarding the supervised, we have two categories. We can provide exclusive of overlapping clustering. And we can harness this to our own benefit in QAM signals. So suppose we have this QPSK received constellation diagram. With hierarchical clustering, we can do nonlinear, we can provide nonlinear decision boundaries. While with k-means clustering, we can have hard clustering, exclusive clustering. So the two algorithms, the first algorithm we're going to implement here for equalization, for enhanced equalization, is the k-means clustering. So in simple words, k-means clustering is a way to group similar things together into different clusters, but each element is assigned to a single cluster only. And we do that. Initially, we set some centers. So this can be data-aided center, or you have some information about that in the initialization process. And then in each symbol, we calculate the minimum Euclidean distance between the center and the symbol. We do for all symbols. And then we cluster them. After the clustering, we take the mean of that, and then we repeat the process depending on the number of iterations of the algorithm or until it is converged. There is the other algorithm we call it, it belongs to the probabilistic clustering algorithm, is the fuzzy logic C-means, and it can be well understood through these two diagrams, which express the membership degree over the number of symbols. So in hard clustering, we can see that all symbols belong to a single cluster only, so it will be 1, 0, 0, 1, and so on. But with C-means, each one is assigned to multiple clusters with a different membership degree. So, for example, if we have the symbol point here, this might belong 20% to the other red cluster. And with this way, we can provide nonlinear decision boundaries, which are highly desirable when we have high nonlinear phase noise, as like this one in this 16 QAM noisy constellation diagram. Okay, so now going to test the terahertz optical wireless communication system, we will apply the machine learning algorithm directly to the receiver DSP. So what we're going to do is we're going to have the linear DSP and then just simply add an extra DSP block there. So after the electronic data signal in from the ADC, that will be typically a 2 samples per symbol. We provide the chromatic dispersion compensation algorithm, clock phase recovery, then time domain equalization. You can have a simpler one like 2x2 MIMO just to remove polarization mode dispersion from fibers, and the other polarization effects also via the antenna and due to random potential barrier regions. And then we go down to 1 sample per symbol for the transceiver noises, which will be the carrier frequency offset between transmitter and receiver lasers, and the carrier phase noise, carrier phase recovery with an algorithm like Viterbi or the blind phase search algorithm. Then we have the machine learning algorithms and then symbol detection and BR estimation. So here you can see some of the parameters where FLC is the fuzzy logic clustering. And for DNN, we didn't choose a very complex model, so that was of 6 hidden layers and 12 neurons. And for nonlinear activation function, we have chosen the ReLU, the rectified linear unit. So this is an example of the received constellation diagrams. We have a special approach on DNN because in other research papers, if you have seen how they implemented, they suffer from the jail window constellation diagram because they separate real and imaginary part. Here in a common DNN, we take both real and imaginary parts and we account from the cross information. So we have a type of equalization from the nonlinear phase noise. Regarding the clustering approach, we have only clustering decisions. So there is no equalization, just final decisions for BR estimation. And that's why we typically see most of the symbols here allocated to the final near the centers cluster symbol. So taking the exact previous schematic diagram. So after the receiver DSP, we can see here an example of bit error rate of 0.04. And we have all these nonlinear phase noises with non-Gaussian shapes. Now we can have more Gaussian shapes, and we can improve the bit error rate here to 0.02. So let's see now also some results in terms of the wireless link distance, which is very interesting. So first, the DNN significantly outperforms the linear equalization, but also the clustering algorithms, which provide relatively marginal performance improvement over linear equalization. At optimum 800 meters, we can extend DNN can extend the wireless distance by 135 meters. Also, keep in note that at lower wireless distances, because of the LNA, as we mentioned earlier, DNN can have remarkable BR reduction because eventually it can recover this non-Gaussian received constellation bin shapes. And so DNN actually is the best algorithm, but it is more complex than the machine learning clustering algorithms. And so this is a very good application here to further improve performance. So in conclusion, terahertz communications are indeed a very good technology when we would go to very high data rates and there is a demand of very high bandwidth and much higher than 5G. However, when we move to high order modulation formats, we will have much more nonlinear phase noise, and the main problem comes from the low noise amplifiers. And so standard DSP cannot effectively recover for that. And we have shown here through our machine learning framework that machine learning-based equalization can improve towards this effect by managing very well non-Gaussian noise. So thank you very much. I would like also to acknowledge the two projects, AI-Net Protect and SustainNet Advance, two German-funded projects. Thank you very much.